A third of Latvia's population live in this beautiful capital city by the water. But although you'll find breathtaking virtual tours of Riga on YouTube, only EPIC can help you explore one of Europe's leading photonic centers of excellence. They specialize in materials research, but I'm actually extremely impressed with their work on adaptive optics, one of my passions. I want to visit their labs and witness the experiments firsthand on wavefront sensors and high-speed laser metrology systems. So on February 9th at exactly 4 p.m, join us for another epic virtual tour. We've got exclusive live access to the Institute of Solid-State Physics at the University of Latvia, where over 100 highly skilled doctors of science are working on solutions that our industry needs. And as usual, I will be asking them the epic question. I wonder what their answer is, but knowing Riga, we should prepare to be surprised. Ladies and gentlemen, we are live. It is 4 p.m. in the beautiful city of Noordwijk by the sea in the Netherlands, and I'm connecting live. I'm connecting live with one of my most amazing, beautiful, and desired cities in the whole universe, Riga. I'm connecting live with Anatolis Sarakovskis, Deputy Director at the Spectroscopy Lab. Anatolis, good afternoon in Riga. Thank you very much for this amazing opportunity. And the sentence is...
Hello, EPIC community. My name is Anatolis Sarakovskis. As you mentioned, I am Deputy Director of the Institute and Head of the Laboratory of Spectroscopy. It is my honor and pleasure to welcome you all at the Institute of Solid-State Physics, University of Latvia. As you probably know, the Institute is located on the riverbank of Riga, of Daugava, the river that flows through Riga, capital city of Latvia. Institute is a 5-floor building, and we are currently on the 5th floor, where 2 laboratories are located, namely Laboratory of Chemical Synthesis and Technologies and Laboratory of Spectroscopy. Recently,
this is fascinating. So we just entered in the room, you are walking through me, and I can see actually already clean room environment. This is all clean room area?
This is not clean room environment. Clean rooms are located on the 1st floor, on the ground floor of the Institute. But the rooms of the Laboratory of Chemical Synthesis are also quite clean. So these are open access laboratories. If you have any idea of synthesizing sample, if you want to anneal it at different temperatures in different environments, if you want to make characterization of these materials by different techniques like X-ray diffraction or scanning electron microscopy, this is the right place to start.
So you're looking for industry cooperation. So anybody who needs...
Yes, sure. The laboratory serves the needs of the Institute, other academic institutions, and also targeting the industrial partners. Yeah, exactly.
That's fantastic. Already we had the first opportunity for all the EPIC members, universities and industries. If you need to have tested spectroscopy-wise, you need to measure the fluorescence of any material, you have to go to my friend Anatolis. What's next? What are you going to show me now?
Exactly. So in recent years, now we are actually in the room of Laboratory of Spectroscopy, and in recent years, the scientific infrastructure of this laboratory has improved substantially. We have obtained new modern equipment, and this is X-ray photoelectron spectroscopy equipment, which is used to study the structure of different materials, particularly thin films and coatings for different photonics applications. And the scientific interests of the laboratory lie in different fields. One of them is detectors of ionizing radiation. Okay. And in this laboratory, we have thermostimulated luminescence measurement equipment that is used for characterization of detectors for ionizing radiation. Ionizing radiation creates defects in solid-state materials, and you need to have equipment to study these defects. Optical spectroscopy is a very nice tool, but another tool that we have, which is also very useful and can give detailed information, is electron paramagnetic resonance equipment. It has also been acquired just 2 years ago, and now we have it. So we move, and now
can we see it? Can we see it?
Yes,
Let's
yes,
see.
here it is. This is the operator that is sitting, and you see a huge magnet which generates magnetic field to study the structure of the defects, the origin of these defects, and also evolution.
So we are here characterizing detectors mostly.
We are characterizing materials prospective for detectors. Yes, exactly.
What kind of materials are you interested in? I normally say I pay for the shipping expenses of any sample between members, and I don't charge it to my company. So what kind of materials would you be interested in having tested there?
Well, this is a really, really different materials. Materials that are used, for example, in Eurofusion project. These are oxides, aluminum oxide, magnesium, aluminum oxide, and a lot of them.
Okay, so any company that makes any kind of 3,5 alloy, germanium, oxides, anything, this company is interested here in Riga to make the characterization of them and the ionizing radiation testing.
Yes, exactly. You are completely right. Another scientific interest that we have in our laboratory is related with so-called upconversion luminescence. This is the process in which photons of lower energy are converted into photons of higher energy. You might ask, who needs this? And I will answer you, if you want to visualize, let's say, infrared radiation, you have a very powerful laser and it generates light in the infrared region. You cannot see it by your eye, but if it is powerful, then you can damage your skin or you can damage your eyes. You need some material that visualizes this radiation. And upconversion luminescence as a process is a very powerful to do the job. We have developed one composite material that currently is going to be a product that we are hopefully will someday sell. Yeah.
Tell us about the characteristic of the composite you have developed. Come on. A little bit, a teaser. I know there's a lot you cannot say, but just a teaser so I can find some cooperation.
It is a transparent material based on polymer, and we have nanocrystals, nanofluorides in this material incorporated. I cannot say you much more, but yeah, this is something that
we have a question because actually I brought some friends with me. I always travel with friends. I have a friend coming from New York, Malcolm Humphrey from PLX. Malcolm, what's on your mind?
Yeah, hi. I was just wondering what sort of response time you're getting from this material, from incoming photons to luminescent photons.
Response in what terms? What terms do you mean?
Rise fall time. So is it nanoseconds, picoseconds?
No. For upconversion, it is microseconds, or the decay time is in milliseconds.
Okay.
Yeah, but we actually still.
PLX is actually a very interesting partner for you because they have actually brought many different optical elements to space applications. It's one of our key companies in this segment, so it's a clear partnership here. But please continue.
Yeah, we do actually study materials that are much more faster. We study scintillators, and we have powerful tools to do this. We have picosecond and femtosecond lasers that can excite the luminescence, and we have streak camera, fast streak camera, and time-correlated single photon counting system capable of detecting the luminescence decay times in the order of tens of picoseconds. But this is completely different application. These are scintillators. Scintillators for medicine applications and scintillators for example, for experiment at CERN.
When it comes to the single photon counting here, what kind of cooperations, what could be the ideal partner you could maybe start something working together?
I think that anybody who needs to detect the luminescence, fast luminescence, we are open for the cooperation. In the spectral region, okay, maybe this defines somehow probably from 250, 300 nanometers up to 800, 850 nanometers.
Fantastic. We'll find you some nice partners.
And very nice. This is vibration spectroscopy laboratory, or should I say room. where we have Fourier transformation infrared spectrometer and state-of-the-art Raman spectrometer equipped with a confocal microscope. They are mostly used for academic research, but you know that Raman spectroscopy in the shape of surface-enhanced Raman spectroscopy can be used for very applied things like sensors for medical applications and environmental sensors.
Of course, the Raman spectroscopy has actually emerged quite recently for the agriculture, growing a lot. But what I have seen here so far is that Riga, the university, we're going to ask later the director, is very well known for the material research side, and you had developed there in that corridor a huge set of equipment to actually do the characterization almost of any material for almost any application going up to harsh environments. So it is quite incredible that we can actually bring many cooperations here. Thank you so much.
Yes, and the final room that we have here is the room where we have a spectrophotometer, where we have one operator currently working for general characterization of optical materials, and for more advanced characterization is spectral ellipsometer, which is a very nice tool to have for thin films and coatings, so optical materials of this kind. And if I want to summarize the equipment that we have and our possibilities, I should say that the laboratory of Institute, the laboratory of spectroscopy, has unique feature. We have a lot of different spectroscopic equipment within one hand's reach. We are open to collaborate with different academic institutions. We are open to collaborate with industrial partners. And I hope that, I mean, you have seen just one floor of 5 floors. These are not all the capabilities the Institute has. I hope that someday you will be able to come and have on-site visit of the Institute. But now I would like to give the floor to director.
Wait, I need to put my tie properly. I need to be dressed properly. We're going to meet the director of the Institute.
Yes,
Martin,
exactly.
good afternoon. How are you?
I'm fine, but I have no tie on me, unfortunately, as you have.
Thank you so much for hosting me in this amazing part of Europe. Thank you very much for making this possible. I just saw the corridor with all the different testing, material characterization solutions offered in the spectroscopy sector. And now I have the chance to talk to you, and maybe you can tell me a bit about how this concept has been developed in this area of Riga.
We are institute for more than 40 years in solid state physics, but solid state physics means a lot of material science also, what we do. Of course, all materials, usable materials, mostly are solid. So it's easy to understand how solid state physics goes together with the material science. We started in Soviet times, and then was a lot of material issues with different actions in Soviet industry and space. For instance, we have solved problems with spaceship illuminators in these days before, and as well we worked on different other parts of, I would like to say, some Soviet military complex needs. And a lot of these investigations and things was based on photonic materials and materials for photonic things. So we're feeling very much as a part of photonic community nowadays as well. And mostly we are working, as I told, on material research, but and you saw virtual tour by Anatoly shows a beautiful equipment what we have for spectroscopic characterization in different parts of spectra and time scales. But in the last years, we also noticed that we need more touch on application side of our materials developed by our institutes, investigated by our scientists, and characterized by our scientists. And we started to develop also some capability to manage and build devices out of our materials and out of our knowledge in these materials. So we developed clean rooms with fabrication facilities, and everyone who is interested could look in our homepage. There is some.
I saw the
short.
facilities. It's actually quite amazing, quite amazing. And when I heard your speech and also Anatoly's, I could understand that what you do is to provide fundamental and at the same time applied research in cooperation with industry. How are you going to do that? Because at the end we are talking about very fundamental material research but very clear industry applications. Is there any particular plan, a strategy to attract companies to work with you?
Actually, all our premises are open access. We are inviting every collaborator, even if it comes from industry or from academy, to use our premises. And that's a general plan, because the equipment and maintenance is very hard for small SMEs to keep that expensive equipment in their custody, so they have to use our equipment. And as days goes by, the pieces go smaller and the equipment more expensive. So we must share this equipment, academy and industry, and use a lot of things in common. And also we must share also our knowledge, because the industry quite often have no knowledge in particular material science fields, and we are very long time developed knowledge in that part. We could do a lot of good things for the industry.
We're going to see in a second the wavefront sensor. We're going to see in a second the other capabilities that you can do. But I'm very interested about the industrialization of technologies, because you are developing, as you say, a lot of knowledge. Is there a particular way to create some spin-off? I love this. Spin-off companies, startups out of this cooperation between the university and the companies.
Yeah, actually, we have developed some special division of Institute for Cooperation with Industry called Materialize, and they are working with intellectual property issues, starting some startup companies and so on. So it's very important that this unit is some single point of communication with industry, so that everyone who have a problem or interest in collaboration with institute have to go to special people who are developed skills and understanding how to communicate, and this materialized unit is heart of our communication with industry. At the same time, I would like to say these two examples of devices are really come from our institute, and it is some examples how our knowledge, in the first case, it is in some optics knowledge in optical processes and things, and another one, infrared sensor, is a pure material science product. So how we see, we will go to transfer it in some devices and applications. And of course, we are open to give away our knowledge and IP to industry who is ready to adapt and commercialize it.
Martin, we are going to live now in the coming years a huge push for high-end material development because of all the new knowledge we are developing with quantum technologies. And I have seen a lot of single photon setups, and I also know from many of your team that the quantum technology is something that you want to look very carefully. Is there a particular program for quantum technologies in a particular specific strategy that you are following?
Yeah, we have started with our authorities. It will be soon some quantum program, quantum technology program in Latvia, developing quantum technologies, and mostly we are based and thinking about photonic quantum technologies. And partly we hope that we will get more involved, and of course we are very open to collaboration and giving our premises also to people who would like to do such research within our institute, and in case of some needs of companies for some material research and things related to quantum technologies, we are quite open to collaboration.
Martin, do me a favor. As soon as we can travel again, as soon as we are vaccinated and it's safe, I'm going to Riga and we're going to have dinner together. And I'm going to tell you about some ideas that I think you, with the setups that I have seen, there's a huge opportunity in the quantum technologies for the defense sector. I think a huge set of opportunities that we can discuss. But Martin, it's been a pleasure talking to you. I really can't wait to see the labs now. So let's go to see the labs. And I think the next step is for me to go to see the wavefront sensor team. Sergei, Geertz, Varis, good afternoon.
Hello, dear EPIC attendees. We are Project MATX, dedicated to development of the wavefront sensor. I am Sergei, the leader of the project, and today, together with me, is our business developer Geertz and researcher, optical engineer Varis.
I'm following your advice. They are wearing the mask. They stay healthy, stay safe. This is great because I can't wait to travel again. What are you going to show us?
We have the two sets together to briefly explain you what we are doing. And probably you know that atmospheric turbulence is a major concern in astronomic application and also in free space optical communication. And there are classical means called adaptive optics to correct the atmospheric turbulence. Typically, they rely on two key elements. First is a wavefront sensor to sense the error, and a corrective part, which usually is a deformable mirror, microelectronic device or a piezo-based device. And in our project, we are developing a bit different sensor, which uses phase retrieval. Why? There is always a challenge for developing a more sensitive, more specific for a niche application wavefront sensors. And this is the way we are going, the thing we are developing. Now I give a word to my colleague Geertz to give you a brief explanation about the applications.
Thank you very much. Before we give the floor, I have to ask, when you show me the deformable mirror, is that something that you manufacture? Is that something that you are looking perhaps for another potential supplier? What part of it you do? What kind of things the others can do for you?
This is a off-the-shelf mirror, the old one. I'm just showing it, just to show you how it looks like. And but at the moment we are developing a mirror ourselves for a specific reason, for amateur astronomy. Basically, it will be a specifically designed large mirror with a not large elements and not large strobe, specifically designed for our system.
Fantastic. If you're looking for cooperations there, in EPIC we have companies like Imagine Optics or Phasics that they do fantastic job, and I'm sure we can do some cooperation with them.
Yes, hello.
Hello
everyone. I will tell a little bit more about the potential applications where we can apply our system. So we are now
we have the cameraman in front of him, in front of you. I'm going to ask him a favor. This is live. I want to see you because you look fantastic. I also want to see the setup a little bit. So sometimes he can show us a little bit. Yeah, that's fantastic. Thank you so much. Okay, please continue.
Yeah, we will actually show you a little bit more about the setup. But I will tell you, so we have identified two applications. So first one is, Sergei's already mentioned, amateur astronomers, and we are actually redesigning one of these setups into a simple plug-and-play adaptive optics kit for amateur astronomers, which will allow to lower the turbulence effect, and also with a relatively small investment increase the existing telescope performance for the amateur astronomers. And for example, if you think about astrophotographers, then they would, with this easy kit, they have opportunity to decrease the space observation time, but at the same time, they will be able to achieve much better images, astronomical images. So this is one. And the second one, this is free space optical communications, where we have submitted European Space Agency proposal in January this year, and with the aim to actually investigate, validate, and test if our phase retrieval wavefront sensor would be applicable for the future ESA missions related to free space optical communications. For example, there is a so-called Skylight program, which is dedicated to free space optical communications. And we also know that atmospheric turbulence plays a significant role and affects free space optical system stability, data transfer speed, and the existing Schack-Hartmann wavefront sensors are not effective enough, and they are too complex, and these systems are too costly. But without with our existing technology, we believe that we can make reliable, fast, and relatively non-expensive free space optical communication.
This is a huge market. The market of FSO for space communication is one identified by EPIC as one of the ones to watch, and many companies in this sector on the development of transceivers as well, the laser communication, they are actually growing a lot. But you know what? I never travel alone. I hate traveling alone. So today I brought friends, and actually I brought Imon Murphy from the European Space Agency with me. Imon, good afternoon.
Good afternoon, Jose, and also to Latvia.
I'm quite amazed what they are doing here in Riga, and I was very interested in seeing this setup because they are talking about adaptive optics for FSO. And I don't know, we have been talking quite a lot about integrated photonics coming to this market. We have been talking a lot about being shaping for this market. What is perhaps some advice, suggestions, or anything in your mind to tell my friends in Riga?
Well, I think the first, excellent work, great. I think the next step is to investigate through the Skylight program, since you mentioned it several times, to explore what Riga or what Latvia has as a main driving force, which would be of interest, primary interest to the Skylight program. That would be the first thing.
Yeah, this is what we plan. We have a submitted proposal. This is type A, feasibility study application. We see whether we fit, and then we can go the next step to really, test and partner with other companies in these calls for the Skylight. But
yeah,
ladies, gentlemen, we actually wanted to show you something. How they
Please show us.
So basically, I will pass the floor to my colleague Varis, so he will tell about one setup, and then Sergei will come back and show how the other setup works. Let's go, Varis. Floor is yours.
Hello, all participants. What you can see here is an optical setup used initially for developing the new kind of a wavefront sensor. And this optical system has undergone many different modifications, studying both biological and astronomical objects. And what I am going to show right now to you is a phase retrieval of a turbulent atmospheric layer, or the so-called Composite phase screen. So in essence, what we have here is a plane wave originating from a fiber collimator and illuminating a Composite phase screen designed in a photoresistive layer using grayscale lithography methods. And we insert our object under study here. And next, we apply an algorithm called phase lift, retrieving the phase of an object from coded diffraction patterns. And I will show you an example of coded diffraction patterns shown here in the computer screen. And you see a very bright central spot surrounded by much dimmer, higher frequencies. Mm-hmm. And in order to retrieve the phase of an object from such patterns, you need to modulate the object under study by some kinds of masks, and of course you can use a spatial light modulator like here, but you can also apply some thin film technologies and binary lithography to design such a kind of mask. And
Okay.
This mask can be successfully used when rotated in 4 different positions to retrieve the phase successfully. Of course, you could also modulate the object under study using different kinds of methods. For example, rotate spectrally separated object beams relative to the mask, but it all depends on application. And
for the development of that, the development of that mask is extremely interesting. I have seen, well, I have told that next time I go there, you're going to show me the clean rooms. Is that something that you do all internally? Is there perhaps some room for cooperation with other companies, experts in lithography masks?
Excuse me, could you repeat, please, the question?
I see the mask and you're super excited with it, and I love seeing it in your hand. I wonder, do you do this all yourself? Is there some room for cooperation with companies in EPIC specializing in optical lithography and masks?
Yes, I have designed on my own, but maybe I see some cooperation, and if someone is interested, I would be very excited to share my experience in designing such kind of masks. And yes, the method is straightforward. You need to use some coating technologies to put thin layers of chromium and copper, and next apply a photoresistive layer. And I think if some clients are interested in this technology, they could the production of such masks could be invented, and it could be produced in large mass. It could undergo mass production.
Of course, I'm calling for the EPIC members like DMP or Photomask or EVG group. Here, there is perhaps some room for cooperation on the designing of this mask. Show me something else. I can't wait.
Okay.
So I see the Orpheus laser there.
Okay, actually, I need to give the word to my colleague Sergey, and he has even more something to show you to demonstrate the reconstruction of point spread function and so on. I will give the word to my colleague.
Thank you so much, Boris. Sergey is my man, looking fantastic in blue, my favorite color. What are you going to show us?
So this is a different setup, and it's a very simplistic system which allows us to show you a phase retrieval, how it actually works. We have a beam coming here, reflected from a deformable mirror on a beam splitter and going into the sensory part. This system is specifically unique. It does not use any specific elements, and we are proud of it. So right here you see adaptive optics testbed, and we see a point spread function which comes into the system, is sensed. Sorry, somebody touched the system. We retrieve the signal and we retrieve the phase of the signal. Of course, we have a specific metrics typical for adaptive optics, like root mean square of aberration, Strel ratio, peak to valley, and here we put also the mirror signals. So in this set, we are manipulating with a very low amount of Zernike coefficients. You can see that also only 5 pieces here, and by changing the values of the mirror, we can see that the phase changes, and we can sense it. There is a specific element here, which is a Kolmogorov phase mask. And in the next steps of this design, particularly, we will use it to estimate the speed of the system. This is what we are working now, because the system speed is not optimal yet. So we are working on to get it running fast. That's basically all. Thanks for your attention.
Thank you so much on this. I always come with friends here, so I actually brought somebody from Optosigma with me because they are really one of the key companies that we have in Epic in optics, from filters to any kind of mount for the optics. I think there could be some room for cooperation here. Hugo Driux from Optosigma, welcome to Riga. Do you see what they do? Is there any perhaps some room for cooperation here?
Hi, thank you so much, Jose. Hi, I was just wondering, so I saw you have a great setup and everything else, and I saw that you're using cage systems, and I was wondering the choice between alignment and stability that you were made in terms of aligning all your system with cages.
We prefer cages, and we had also elements without cages, but somehow we like them. Sometimes I cannot say we experience any trouble with it, so it's enough for us.
Okay, good, thanks. If you need anything, let us know.
One of the big problems, wait, Hugo, because one of the big problems that we have with the deformable mirrors, it is especially in these kind of setups, when you are actually taking the setups to other testing facilities, is to guarantee against vibration. And one thing that Optosigma is doing really well lately is to actually design these optic mounts without the optic holders. So holder-free optics, which I do believe here for some of the targeted applications that you are doing, especially in the targeting the skylight project, there is a room for cooperation. So I'm going to introduce the two of you offline because I do think that this is one of the ones to watch. But Hugo, stay on because we're going to go now to another setup. What's going to happen now? Because thank you very much for showing us this, but I was told that we were going to see some thermoelectric sensors and I didn't see them yet. So where are you going to take me now? Oh my God, I think we're going to go somewhere serious again. We have a person holding something that looks like a thermoelectric sensor. So I'm in business now. Hello, good afternoon.
Hello, my name is Kaspars. I am a researcher at the Laboratory of Organic Materials in Institute of Solid-State Physics.
Hello, Kaspars. I'm Jose. I'm a geek of photonics, and when somebody shows me a device like this, I get super excited. This is what do you have in your hand?
Yeah, we have in my hand. I have a prototype of thermoelectric sensor, high-speed thermoelectric sensor. We have spent several years in research of thermoelectric effect in organic materials, and it resulted in a prototype of proof of concept prototype of high-speed thermoelectric sensor. The unique thing of this sensor is the combination of material properties. The active thickness of the layer is half the micrometers, and it ensures that this heat capacity of the sensor is very low, and thus allowing this sensor to operate in high-speed performance. This sensor has a broad spectral range, like thermoelectric sensors. We have tested them from UV light with excimer lasers, like 180 nanometers, till infrared radiation with 2.3 micrometer wavelength and more. With appropriate heat absorption layer, it can also measure individual pulses of CO2 lasers. So this sensor rise time, signal rise time is below 10 nanoseconds, and the response time below 1 microsecond. It allows us to determine individual laser pulse up to repetition rate of 1 megahertz. So this sensor combines the high-speed performance of photodiode and broad spectral range of classical thermocouple detectors. So this technology could be used to make the instrument that can substitute several sensors. It can be used as standalone laser power meter for laser manufacturers or laser processing service providers in production or quality assurance testing. It can also be built-in, like built-in unit in laser systems for laser marking, medical systems, or other laser processing systems. So I think now we can proceed with demonstration. here we have that.
Before we see the demo, because I always want to do cooperations. You mentioned that you want to interact with companies who manufacture CO2 lasers. You make sure that that you want to manufacture with companies that make any kind of laser and do the characterization. I never travel alone, and I brought with me one of the key companies in EPIC in laser system manufacturing and workstations manufacturing. Stankiewicz Valdemar from Elas in Lithuania. Good afternoon. Stankiewicz? Yes, good afternoon.
Good afternoon. Yes.
Acho for answering the phone. Thank you very much for being with us. We are about to see the thermoelectric sensor from Riga. The idea here is to understand what is needed for the laser industry. Elas is the key company that we have in workstation manufacturer. So as a workstation manufacturer, what do you expect from a sensor to identify the beam intensity of a laser?
Okay, so let's for me introduce myself. As Jose mentioned, that we manufacture laser systems for various applications, from cutting to drilling and texturing and so on. And for some cases, we need some sensors. I am not sure what sensor is this one, thermoelectric, but in some cases we need to sense temperature of our samples on the surface and quite precisely. So if I think about this sensor, so
Stankiewicz, I'm not sure what they're going to show us either, because I will say I want to be surprised. So let's see what they show us, and then after I come to you, and I also come to Expla. Konstantinos is also here, and we try to see if we can do an epic cooperation. Tell us, show us something cool.
So, okay, here we have a tunable wavelength laser. Now it's tuned to 1 micrometer of wavelengths. I will show that we are irradiating.
Should I wear glasses too? I forgot my glasses.
You will be fine. So now we are irradiating the sensor, and we see that actually this the signal and the rise time of the sensor actually is quite below 10 nanoseconds. It detects this laser pulse, and the fall time of the sensor is below 1 microsecond. And now I will tune the laser for 1.5 micrometer. So to show you this wide, broad wavelength sensitivity. And now the laser is tuned to 1.5 micrometers, and we still see the signal. That wouldn't be possible with classical photodiodes because they're not sensitive in that range. So yeah, this is our test sensor prototype. So thank you, and we are welcome to answer your questions.
Quite amazing. I don't know if doing applause like this looks cool, but only if my friend from Expla, one of the key companies in ultra-fast lasers in EPIC, finds it useful. I will give you the full applause. Konstantinas, you just saw what they can do, and they can use very, very simple oscilloscope. They actually could visualize with a very low-cost sensor. Does it make you excited? Is there room for cooperation here?
That is, I'm very excited to see that this is Expla laser that we are testing. So, so I'm double excited. And I know that he had some previous contacts. So this is the technology that we are keeping our eye on. So that's really great. I am excited.
Thank you very much. In short, you already know Expla because you bought the laser, but when it comes to a cooperation on the testing, we have had lots of different events on beam characterization and laser output characterization. There is a lot of room for cooperation here. I also would like to ask you, so you had this thermoelectric sensor in your hand, it's fully developed. On one hand, you have developed, especially deposition is all done, as I understand, in the clean rooms in Riga. Is there any room for cooperation for the further manufacturing of these sensors and the further industrialization? What is the next step? As a friend of mine always asks me to ask, what is your preferred future?
What is preferred future? Of course, to commercialize these sensors. At the moment, we are fabricating this sensor without coating in our institute, but we are not. We are, let's say, very well developed this active layer. But for these absorber layers, we are taking this process from other companies. So the next steps for this production or commercialization would be to produce this sensor reading part. At the moment, we are using the oscilloscope, but for let's say for this laser power sensor, this application, we need to develop this electronics of this readout unit for the sensor itself.
Yes, I never travel alone. I brought friends with me. From Fraunhofer FEP, which is one of the key institutes in EPIC in the sensors and the display sector, I have my friend Uwe Vogel. And the reason why I want him to be now with us here in Riga, welcome to Riga, Uwe, is because I really think you can share, Uwe, maybe some ideas on what should be the next step. The sensor is developed, the sensor is tested with different lasers. What do you think they should do to go towards the industrialization?
Well, I mean, that's let's say mainly also one of our aspects or major aspects within Fraunhofer to actually transfer it from, let's say, from science into industry, into commercialization. So, and therefore, what Jose mentioned is obviously one of the next critical and important steps. I was wondering, for instance, on this kind of specific sensor, the sort of organic materials that you mentioned. So one thing, for instance, is how can it be produced? Is it a cheap material? How can it be processed? How can it be made reliable? Those questions would be, let's say, the next questions I would ask.
Okay. The main active material is an organic material. It could be synthesized, and with organic materials, the good thing is that if you synthesize in a large quantity, it gets cheaper and cheaper and cheaper. So the material availability wouldn't be the problem. So, and this actually this sensor manufacturing process could be realized in one vacuum chamber. So we think that this fabrication process also could be quite easy and cheap.
I think one sector, Uwe, that we target, of course, also well, the industrial laser-based manufacturing. Validation is key, right, Uwe?
Sure. I was just wondering, the organic material, is it an organic semiconductor?
Sorry, could you repeat the question?
The organic material, is it an organic semiconductor?
Yes.
Yes, it is organic semiconductor.
Tell us more about the material. Come on, don't be shy. We will not tell anyone.
Yeah, okay. This is a low molecular weight compound, tetrasthiothertacene. So it has very good properties that it is quite stable till 200 degrees per Celsius, and allowing us to use it in such application where it's heated up by the laser radiation.
Okay, and maybe for commercialization, it would probably be interesting to manufacture it or to process it on larger substrates, for instance, on wafers, 8-inch wafers or something like that. Is it something you can imagine? Or if not, maybe this is something you could help with.
At the moment, we are processing them on 2-inch wafers.
Okay.
But technically, there wouldn't be the problem to expand the size of the target. Yes, these wafers. One thing that maybe I didn't mention, that this technology has good properties that actually in these sensors, the sensor active area size doesn't affect the high-speed performance. So it allows us to make various sizes of sensor with the same high-speed performance. That is a quite unique property, I think, that couldn't be done in semiconductors and other type of sensors.
Okay, thank you very much.
One thing that I always wonder, Kaspar, when I see a sensor in your hand, and then I have all the companies here next to me, is about TRL5. It's about testing this in the right environment. It is about having the right partners for that. I do have many companies who have done this in the past for space applications, also for the industrial-based manufacturing. What kind of partnerships could we start today for this? for the validation and testing of the sensor in the right environment. It works beautifully in your lab, and I'm sure it's going to work also beautifully at ArcelorMittal or at Audi or at the companies who want to test.
Yeah, at the moment, we are at the stage where we are fabricating the series of these prototypes. And in the soon, I think in the next week, we will be ready to send them to our potential partners and interests for testing. So in the soon, we hope it will also be validated in the environment, actually, yeah.
All right, my favorite part of the meeting starts now. This is when we have a round of questions, not only for you, Kaspar, but also for all the people who presented this fantastic center in Riga. And the first question is coming from PLX. Malcolm Humphrey, what's on your mind?
Hello, yeah, I was looking at your sensor. I was wondering how it compares with other sensor types in terms of noise and responsivity. Is it as good as APDs, for example?
Kaspar, how does it compare to other sensors?
Okay, if you're looking on this sensitivity, then the sensitivity and the noise is, let's say, it could be comparable with like a coherent USB Max Pro sensors. Of course, there is some more sensitive sensors, but as it is based on this thermoelectric technology on thin films, then I would say, okay, about maybe it's hard to compare, but if you are looking for this noise is compensation, then I can say that we can detect the impulse with the energy about 1 microjoule and a little bit less. At 2.5 microjoules, we achieve this signal to noise ratio to be 100. So yeah, I can say that kind of number.
So what applications do you see for it?
We think it could be used to fabricate this laser power meters for monitoring the laser stability, to use it in different laser process applications like laser marker or maybe even medical systems.
Okay, thank you.
Thank you very much, Malcolm. I think there is some potential room for cooperation here. I would like to take this really offline. This is what I love the most about the EPIC meetings. I would like to ask now my wavefront sensor friends. I am very excited about what you're doing. Very, very excited, actually. I have seen many setups around Europe on this, and many of them actually targeting a different market, the market of ophthalmology and the market of bioimaging. Is that a particular application sector that you have foreseen on that? Is that something that you would like to explore further?
Sure. We foresee it in some future steps. Well, originally, we been in adaptive optics for retinal imaging, which is quite a biological application. And when this sensor will be, tested in many ways, because now it has a general form, and we are adapting it for specific niche. The next step for sure would be to go for biological application.
One company, because at the end of the day, also in the wavefront sensors, one huge push that we have seen lately is the industrial manufacturing. In the industrial manufacturing, companies like Imagine Optic are actually doing quite a lot of work on the characterization of high power laser output. And I can see from your colleague at the Thermoelectric Sensor that there is, of course, a one-stop shop here. So I want to start introducing to companies. Why do you think these companies in the high power laser sector should come to you and do something together?
Yeah, it's a question for us. Eh?
For the man in blue, my good friend, tell me.
Difficult to say why.
Let's broaden the question a little bit more. So all these companies, 660 members of EPIC, today we see the two labs, you do fantastic work. Why do you think these companies should come to you and do something together?
Well, because we are developing a quite sensitive tool, which is adaptable also for specific need. Right now, today I showed a simple system which does not apply many examples or doesn't sense many examples. But the thing Varis is doing is quite sensitive in terms of accuracy of testing the wavefront, which is particularly would be interesting for high power lasers, where a lot of photons and you need the sensitivity to try them kind of very collimated or specifically focused. So I don't see any problems for us to kind of join this field because the sensor itself allows such adaptation.
Okay, I want to go now to my other friend, my sensor friend. Please change to my other camera because I want to say hello to him. I could see that you are characterizing already the laser of Expla. Fantastic fiber lasers. I love this company. I can't wait to go to Lithuania again and see them. There are many companies that are specialized on developing the ultra fast and high power lasers. You were wearing the glasses, the protection glasses, when you show us the working environment, working group. I would like to, I never travel alone. And I have with me from Laser Vision, Lars Schober. Lars, good afternoon. Lars, you know what is the sentence of EPIC 2020? You are muted. I'm going to print t-shirts with that. Lars? Okay, we will come back. We'll come back to Lars. But my question here is, of course, laser safety is very important when you are actually working in the field that you are working. How are you addressing laser safety, and what kind of requirements, what kind of needs, what kind of ideas do you have for a potential collaboration with companies in laser safety?
Hello, how are you?
Lars is here. He's unmuted, my friend from
Yeah,
Laser Vision.
It was a little bit difficult with the technique here. So the technology is not working very well here now.
So as you have seen, we have seen the setup, we have seen the experiment characterizing the Expla laser. He was
and I heard a little bit, but not all. So, and yeah, what we are offering now as Laser Vision is laser safety products. So we have laser safety eyewear, laser safety curtains, laser safety windows. Yeah, more or less for all applications. So whenever you need any stuff for laser safety, then we are the right company.
How do you address laser safety? Do you get the glasses from the provider of the laser? Do you actually know the specifications by the glasses yourself? Is there a facility manager that just gives you the glasses you don't have to worry about? How is it addressed, Enrique? Who is the contact person for me to address this with Laser Vision?
Yeah, you can ask me. So whenever you need anything in terms of laser safety, you can ask me.
Thank you very much, Lars. Yeah. And we are almost running out of time. We only have 2 minutes left. And this is when I ask people about the ideal partnerships. I already asked this question to the thermoelectric sensor part, but the wavefront sensor. After this meeting, I want to start making introductions by email of potential partners. So you could dream away. Give me the Santa Claus Christmas list of Riga in the field of wavefront sensors for collaborations and cooperations. And please unmute the camera as well. You are muted? Yes.
Hi, do you hear me?
Yes.
Yes. The question was about what potential cooperations we are looking for. Yes, so first of all, we are looking for partners who has experience in space optical communications, and specifically in space industry. Because, as I said, this is what we want to we want to research and explore further. And also, second, which is also very important, we are looking for the amateur astronomer companies who are offering services to other amateur astronomers, and they can put their telescopes, basically rent equipment, and they provide services for installation and surveying and so on. And the third is also the companies who are manufacturing and selling different equipment for the telescopes. because this we also see as a potential partners for us in order to commercialize this wavelength sensor technology. Those could be our, let's say, road to the market, like our channel partners who can then push it forward to the customers and our target audience, so to speak.
We started at 4 o'clock, we finished on time at exactly 5 o'clock. Before we go, I'm gonna ask all my friends to unmute their microphones and give you an applause, a round of applause for a fantastic show. You have done an amazing effort on bringing all the potential collaborations of the EPIC members to collaborate with my favorite center in Riga. I honestly can't wait to go there and have a dinner with you. You all deserve it. Keep wearing your mask, wash your hands, stay safe, stay healthy, and continue being epic. Riga is epic. Thank you very much. Bye-bye.